Okay. So hello everyone. In this presentation, we're going to see how a relatively new tool called Ncrack, belonging to the Nmap toolset, how we can use this tool to test the password strength of various systems. First of all, I go by the nickname Thilgor, and my real name is Fotis Hanzis. I'm the maintainer of this site, socro.org. Some highlights of my research. I'm mainly interested in network security. Some of my past work was exploiting the TCP protocol in a work that was published in FRAC 66. It was about the exploitation of a legal functionality of TCP, the persist timer, in order to conduct a large-scale and generic denial of service attack. And another work was the exploitation of the XMPP, which is a protocol that you may have used indirectly because it's the backend for Facebook Chat, Google Talk, and it's also used as an open source alternative for MSN. And this work was also presented last year here in AthCon. And of course, I have also gotten myself involved with Nmap development and Ncrack, which I wrote about 2 years ago. And Ncrack belongs to the Nmap toolset. And these are the ways with which you can contact me. Before I go on, I would like to ask you, I expect to see a lot of hands here because I know that you're all interested in security. How many of you have used Nmap? Okay. And how many of you have used some other tools of the Nmap toolset, like nping, ncat, the Nmap scripting engine, or even Zenmap? Okay, I see fewer hands here, and that's to be expected, because many people still think that Nmap is just a port scanning tool, while like it was in the first version that was published back in FRAC 51. But that's not the truth anymore. It has evolved into a much larger project, and this involves Ncrack, which I'm going to describe now in this presentation. Now, how it all started. Back in November 2008, I was studying a lot about code inspection and code auditing. The book that is considered the Bible for this field is The Art of Software Security Assessment, which has been written by security gurus John McDonald, Mark Dowd, and Justin Suh. And there was a chapter there that specified in networking a list of basic rules that all low-level networking tools that receive packets from the network should obey. These rules had to do with mostly with length validation. So all tools like, for example, Snort or Nmap that receive packets straight from their network without any kernel intervention, using libpcap and or using raw sockets, have to do some basic validation on their own, because the kernel doesn't do that, since we're talking about direct access to the packets. So Nmap sends some packets to do its SYN scanning or OS detection and other functionalities. And there was some validation routines that checked if the IP datagram was valid as far as the length is concerned. So I went and applied those basic rules in these validation routines. And what I saw was that, you can see it here, that the IP datagram length was okay. They initially checked the IP datagram length, which is the length of the whole IP packet, meaning the length of the IP header, the length of the TCP header, and the length of the TCP payload. But when it got this packet from LipiCap, and LipiCap always says the truth about the real value of the data size, it allocated a buffer for the packet, but then continued on and did all the rest of the checks using the field in the IP header. The IP header also has a field that specifies the IP datagram length. But of course, nobody tells us that this specific field hasn't been meddled, which means that it may be corrupted or even purposely crafted. So what I did was craft my own packets, changed this field, and the real data were less in size than the ones that this field specified. So that had as a result that there was an out-of-bounds memory access and all the dire consequences which that implies. The funny thing about this was that in order to be able to craft this packet, I had to do some changes in the Linux kernel, because the Linux kernel, when you use raw sockets in order to craft your own packets, usually allows you to craft and specify every field. But this particular field, and only this, that you can see in the source code in the left, was always filled in by the kernel, perhaps to prevent this kind of abuse. But of course, this can't really stop us, because the only thing that we have to do is just comment out the line, and as you can see there, and then recompile the kernel, and then of course it's everything is done. In the meantime, the FreeBSD kernel does the same thing in another manner. It checks if these values in the IP datagram length are valid, and that you haven't specified it some false values. And if it finds an error, it just returns and never lets the packet out to the network. Of course, we can always do the same, just comment out these lines, recompile the FreeBSD kernel, and use FreeBSD to craft our packets. This can't really stop us. And I mentioned all this because it was my first serious contribution to Nmap. I wrote a bug report and bug fix for this particular bug. Now, after a while, in spring 2009, I applied for Google Summer of Code. For all of those of you who don't know what it is an annual program organized by Google, in which students from all over the world can participate and work remotely from their homes in one of the largest open source projects. There are about 150 to 175 open source organizations, very big names among them: the Linux kernel, GCC, Nmap, various distributions, Fedora, GNOME, KDE, and many more. And the whole project, the whole program lasts 3 to 4 months. The first month is called the community bonding period, in which you don't really do any hardcore coding, but you get to acquaint yourself with the code, the community behind the project, and the mentors which guide you through the process. There are 1,000 students every year, about that number, and of course you get paid for this. Now the stipends have gone up to $5,000, but you get this after you pass 2 different evaluations. which are done by the mentoring organization and the mentor. Of course, you have to, in order to accept you, you have to make a good application form. Your CV, of course, always matters. And if you have a showcase of research or other contribution to the project, like bug reports, bug fixes, or even code writing, these are all positive factors in accepting you. And of course, whoever decides to participate should expect to write a lot of code. For example, Ncrack is now almost 26,000 lines of code. And when I applied for Google Summer of Code for the Nmap project, and after they accepted me, there was nowhere the idea of Ncrack. Usually every organization uses a certain web page which has uploaded all the ideas of the potential projects for the upcoming Summer of Code. And during that time, there was a lot of interest for extending Ncat. Ncat is a modern implementation of Netcat, which is the venerable TCP/IP Swiss Army knife, which you must all have used. And it belongs, of course, to the Nmap toolset. And there was also some ideas about extending the support for raw sockets in IPv6, which is a relatively tricky part. And if I remember correctly, there are 2 students working on this project this summer. So I applied for these 2 ideas, but after a while, I got an email from Fyodor, who is the original author of Nmap, and he told me that, he told me, you shouldn't just work on Ncat. We have some bigger plans. And he told me that after having written NSOC, which is a library for a socket abstraction layer that Nmap uses, that was almost 10 years ago. He was planning to write a flexible and very fast authentication cracking tool called Ncrack. He had even registered the domain ncrack.org, but he never had the time to do it. So he told me, why don't you do it? Why don't you start it from scratch now? And of course I agreed without further ado. And with an email that he sent to Nmap Dev, which is the main mailing list for Nmap development, he sent the initial RFC on Ncrack, and thus Ncrack was born. The RFC was mentioning the general guidelines and specifications on which Ncrack would be built. And as you can see here, the main snippet is that it of course has to be very fast and flexible. It has to support all the basic network protocols like SSH, HTTP, etc. And it must even be faster than its competitors. It also has to leverage every functionality on protocols to improve its speed. For example, in HTTP, it has to use, in HTTP 1.1 actually, it has to use persistent connections and pipelining in order to do many more authentication attempts per connection. And it would need to be written in C++, in this mixed mode that Nmap is also implemented. It's mainly more C than C++. C++ is only used for class organization and the standard template library, which is mainly for things like vectors, lists, and similar stuff. So one may wonder, why did we decide to write a new network authentication cracking tool when there are already others? Well, one of the basic reasons is that nowadays weak passwords are more common than exploits. People still use very weak passwords, like their names concatenated with their birth date or their name of their spouse or pet or whatever. And the other thing is that pre-authentication exploits for major services like Apache or OpenSSHD are very rare these days, especially in the white hat communities. And this is because in order to find a bug and exploit it, there are nowadays many proactive defensive measures like address space layout randomization, privilege separation, stack canary values, which makes exploit writing very hard. And in addition, these major servers like OpenSSH have gone rigorous inspection in their code through many years. Of course, bugs have been found, but nowadays it's much more difficult. In addition, in the Nmap scripting engine, which is a framework which Nmap uses in order to do some network scripting through the Lua language, it has been found statistically that the brute force scripts are the most popular. And another positive indication was in the site sectools.org, one of Fyodor's popular sites, which lists the most valuable and popular security tools, as voted by the security community, of course, are all the top 15 security tools have to do with cracking, either remote or local. And now, as for the competitors, of course, many of the competitors are not very actively maintained, and some are way too old and buggy. For example, Brutus is out of the question, it's way too old. TS Grinder is broken. Many of them have portability problems. For example, Hydra, THC Hydra requires Sigewin to work on Windows, and Medusa, the other famous cracking tool, doesn't really work on Windows at all. And there are also other limitations, like, for example, you can't really do any customization. You can't really do any time fine graining or similar stuff. There are very primitive options as far as this is concerned. Now, as for the THC Hydra, these guys might have been shaken or rattled a bit, because I remember that last year when I was in a security conference called PH Neutral in Germany, I met the original author, Van Hauser, of THC Hydra, and he told me, we had some discussions about THC Hydra and Ncrack, and I remember that after about 2 weeks or so, there was a new release of Hydra, when the previous release was a long time ago. I don't know if this is a coincidence or not, but anyway. Now we have to wait the... Okay. The next thing that I'm going to discuss about is the architecture of Ncrack. Ncrack uses a modular architecture, which means that it's the best way to design such a tool, because you want the modules to be as independent from the core engine as possible in order to be easy to write more modules and extend Ncrack easily. The countdown. And each module corresponds to a certain network protocol. Now, let's see if we have, okay. The core engine is responsible for all the network related stuff. It does all the socket operations through NSOC, about which we'll talk later. And it of course calls the protocol modules when it needs to. And as we'll see later, one of its stronger features is the dynamic adaptation to network conditions, which makes it dynamically adapt its timing. We'll see how this works later. Now, this is an example of how the modules work. NSOC, which is the main library for socket operations. It's also used in Nmap, as I said before. Essentially, it's a library that behind the scene, it uses the select system call. Select, for those of you who know a little bit about socket programming, network socket programming, is just a function that loops over all the open file descriptors and waits for events to happen. So, for example, if you have issued a read request and expect to receive data from the network, then when select sees that the kernel notified it through this open file descriptor that the data have arrived, it will return and tell us that this happened, so we can be ready to move on and process this data. So what Ncrack does is its module consists of a pseudo state machine. It's a virtual state machine, essentially. So it breaks up the connection into several smaller parts. Each of them corresponds to a primitive socket operation, like a read request or a write request. So let's see an example. Let's say that we have the SSH module and we want to do an authentication attempt. The first thing is to send a read request after we have connected, of course, to the SSH server, and grab the banner if there is one. There isn't always in SSH. Depends on the configuration. So when we do that, we expect to, the module issues the read request through NSOC, registers a callback handler, and then returns control back to Ncrack, to the core engine. And then the core engine of Ncrack loops through the other events that potentially other modules have issued a request about, does other maintenance operations, checks if there are new connections to open, and when there is when NSOC notifies it that there's a new event, then it calls that module, and this module then continues to the next state. Of course, it has saved before the state, so that it knows that this particular module instance was at state 0 at first, and then it was at state 1, and so on. And then it will continue like this. Then in state 1, it will issue a write request, and then send the first SSH packet, and so on. And this will go on until the end. And this happens, of course, in parallel, without needing more than one process. You only have one process, and through NSOC you do all the parallelization. Now, the problem with NSOC, not exactly a problem, but it's a fact that we can't use raw sockets, the SOC raw capability, in order to craft our own packets. And this means that we can't really use our own timing algorithm. By timing algorithm, I mean to know when to send more packets, when to open more connections. NSOC sits above, on top of TCP. So TCP does all the dirty work of timing. It's different from, for example, the way the SYN port scanning in Nmap works, where it just crafts the SYN packets, sends them on the network, and then using its own timing algorithms that resemble the TCP traffic congestion avoidance algorithms, but in their own way. And it does that without any intervention from TCP itself. But this is due to the SOC raw power. So now that we are on top of TCP, we have to rely, the only thing that we can do is rely on TCP resets, connection timeouts, and some things, some techniques based on statistics, as we'll see later. Let's see an example. Suppose we open, at first, Ncrack opens many parallel probes. Of course, as usually, up to a point, as many connections you have, the the more connections you have, the bigger the authentication rate is, because you of course do all these things in parallel. And here in this picture, the wider the arrow is, the more the network traffic is. So initially this happens. Everything is normal. Then we open even more connections because we want to increase the authentication rate. And of course, the target replies with many more replies. But after a while, we might see that the normal replies also are accompanied by resets. So something is astray here. The target obviously can't really have so many connections, so it starts responding with resets. Then when Ncrack sees that, it immediately decreases the maximum parallel connections. You can see it here in comparison with this, which was the previous slide. But of course, resets will keep increasing at that time. Ncrack will then keep decreasing the maximum probes, and slowly the resets will diminish back to zero. And when this keeps happening, at some point in time, the system will be balanced once again, and everything will go as initially. But, and of course, we can start increasing the probes again. And this is more of a trial and error game. We can't really be sure when the resets will start appearing again. And there will be some kind of fluctuation. So here you can see a graph of the previous example. I think the upper function isn't very well seen, but anyway, the function below, the yellow part, are the resets, while the upper part, which is a brown color, are the Ncrack probes, which are many more than the RSTs. But you can see in the below part that there is some certain time windows where the function is zero. These time periods, these time intervals correspond to the time where the system is balanced. And of course the question in all of this is, what if we take the mean value of all these samples of the parallel connections that we have opened in order to achieve the ideal parallelism of the open connection? And we'll see in a bit why this isn't as easy as it sounds. Of course, we have only talked about resets. Now, what about the timeouts? The timeouts are much more difficult to handle, and this is for many reasons. One of them is that we can't really be sure if there is a network failure in an intermediary node in the network path that connects our host and the target and the scan target. This might happen at random intervals, and it's quite dynamic. We can never be sure about this. And we can never be sure when the packets will start being rerouted through another node so as to bring back the connection. Another reason might be that we have triggered a firewall. And this is also very classic nowadays, where firewalls might impose a certain limit on the number of connections that we have opened inside a certain time window. And if we surpass this limit, then the firewall will just block our IP address for a time period or even forever, until manual intervention, of course. And of course, the timeouts might also be combined with resets, so this makes it even more complex. And there's also a final reason that is also very frequent, that we have accidentally caused a denial of service attack. And this happens usually when we have opened too many connections and there aren't enough resources on the host, on the scanned target. So now in reality, our metric is not the amount of resets or timeouts, but the authentication rate. The authentication rate is an internal metric that just counts how many authentication attempts per connection, not per connection, per a certain time period, per service we achieve. And the higher this is, the faster we are. But of course, it is connected to the resets and the timeouts that we get, because, of course, if there are timeouts and resets, means that many connections are closed, and thus the authentication rate has been decreased. And one of the solutions is to use a trial and error approach, and we'll see how we can do that. So a proposed timing algorithm that sits on top of TCP, as we said before, is the following. There is an experimentation phase initially, in which we do the following things. First, we keep increasing the parallel probes. We said before the reason why we do this, and it's to increase the authentication rate, because we have many open connections in parallel, and this increases the rate. And then we check for the three following things. If the authentication rate drops, and this means that something has gone astray. If there is an error in the, so we have received a reset or a connection timeout, and if there is, if the authentication rate stays the same for a long time period, if this stays the same, then this means that we can't really increase the increasing the connections anymore will not have a direct effect on the authentication rate. So we don't want to waste any more bandwidth. We want to save our resources. And if any of these reasons, if this, of these cases happen, then we immediately drop the limit of the parallel probes. And of course, we need to do this a lot of times. We go back to number one, step one, until we have gathered an adequate sample. This sample will essentially be some pairs consisting of an authentication rate corresponding to a certain number of open connections. But the question still remains, how do we know that we have reached the ideal parallelism? The answer, unfortunately, is that we don't really know. We can never be sure. And this resembles the problem in mathematics, in complex problems, where you don't really know if there is a local maximum or a global maximum. When you reach a maximum, you can't really be sure if this is the biggest one, the largest. And this is also the case here. So what we need to do is just rely on the gathered samples that we previously described, and then rely on trial and error. And of course, we're always in search of the golden ratio between speed, accuracy, and bandwidth saving. We want speed for obvious reasons. We want to be as fast as possible. And we want accuracy. Accuracy, as far as this is concerned, TCP does most of the dirty work. We don't use raw sockets, so we don't need to make any error checking or just see if a packet is lost and resend it. TCP does all that. But we want accuracy as far as the authentication attempts are concerned. What do I mean by this? I mean that whenever you have to test a certain credential pair, a username and password, you can't, suppose the connection ends midterm without having actually tested them, but you have initiated the authentication. For example, in SSH, you have sent the first packet, which initiates the session. Then you have received some other packet from SSH, but still haven't really tested the username and password. And the connection, for some reason, drops. And this is very frequent. It has happened to me many times in the past. And even if this sounds simple, we have to, of course, retest the whole thing. So save these credentials and retest them in a new connection. And even if this is very simple and sounds quite obvious to do, most other competitors, other network authentication cracking tools, don't do it at all. So if the connection terminates mid-term without having tested the certain username and passwords that were to be tested in this connection, they just ignore it and they lose this pair and never test it, never get to test it, which is of course a loss, a great loss in accuracy. And of course we don't also want to waste more bandwidth than it's needed. The problem is, however, that the network conditions are quite dynamic. As I said before, we can never really be sure about the fluctuations in network. So what we can really do is just rerun the sample gathering algorithm that we previously mentioned at random intervals. And this has to be done all the time in order to compensate for the potential fluctuation in the ever-changing network conditions. Of course, you can also do some customized time fine-graining. For example, you might not trust the dynamic values found by the Ncrack engine, or you might just want to be more accurate in your scanning. So what you can do is the most classic option is the timing template, which is the same as the Nmap uses. Anyone who has used Nmap already knows that there are 5 different templates, from the extremely slow, which is paranoid, to the extremely fast, which is the insane. But of course, you must know that the 4 last options, aggressive and insane, may also cause a denial of service attack due to the flurry of open connections that this will ensue. Some other things that you can do is there are 2 different options in as far as the number of open connections are concerned. The lowercase connection limit, CL, which forces Ncrack to open at least as many as the connections that you specify in this timing option. And there is the opposite of this option, the uppercase connection limit, which forces Ncrack to never use more than the connections that you specify there. And this is, of course, very useful when you want to, when you are afraid that you might cause a denial of service attack, or you just don't want to waste many resources. Another handy option is the connection delay, with which you can adjust the time between each new connection. And there's also another very useful feature that we're going to discuss later, which are the authentication attempts per connection. This means that how many credentials you are able to test and you test in one connection. Of course, there are limitations set by the servers themselves. For example, OpenSSH by default lets you test 6 credentials per connection, or some other FTP servers might let you just 3. And some telnet daemons, I remember from my own testing, might even let you just 1 authentication attempt per connection. Now we'll see a real case scenario, how we can bypass a firewall using these timing options. Now, assume the scenario is the following, that we want to crack at least 1 SSH account of the host Diogenes, which is a cell account server in my university where I study. And suppose this server doesn't listen on the default port 22, but on 45.120. And we, of course, don't want to alert or trigger the firewall. And the firewall rule set is the one that you can see here, that it blocks your IP if you open more than 2 connections per minute. This is quite a strict rule set, as you can see. Now some may wonder, how do you know that this is the firewall rule set if you don't have access to the machine? You can do that by previous experimentation. Suppose that you had tried to open many connections and that you found out that when you opened more than 2 connections in 1 minute, that the firewall blocked you. It isn't so difficult to find. Now let's see some default configurations in SSH, because this we're going to test. The max authentication tries, which is, as I said before, is 6 is the default value, are the maximum attempts per connection that you can do. And the maximum startups are 10. These are the maximum parallel connections that you can open per IP. And we also assume that we want our attack to take place only during the nights, because we want to be as stealthy as possible. Now, as far as the authentication attempts are concerned, Ncrack does the following trick. It strives to learn the authentication attempts per connection that the server lets you do using a reconnaissance probe. This isn't any other thing than opening an initial connection at the very beginning, which is just one connection in parallel. It doesn't open any other connections. And this is to ensure that you have an almost 100% chance that nothing goes astray and that your connection isn't ended midterm. So in this case, that you achieve all the maximum authentication tries. So what do we do in order to accomplish this? Initially, we use the time Unix command, which just tells you how much time the running of a program takes. And we specify that our module is SSH, our host name, and then our port, which isn't the default one. Then we want to impose a limit in the connections, in the maximum connections in parallel. We set this to 1, and we want to do this because we want to have enough time to press Control-C in this case, and to count how many seconds one connection takes. And of course, we also specify the debugging output to be level 6, which is just enough to show this output that you see here. And you can see here that when the connection has been closed, which means it has finished, we immediately press Control-C and close Ncrack. We can also see here that in the supported, in the section where it says supported, we can see this is actually the number that the reconnaissance probe has found out. They are the maximum attempts per connection, as we said earlier. And the time command just told us that each connection takes about 16 seconds. So we assume that this is about 15 seconds, because you must also take account the fact that you can't immediately press Control-C, and there is a delay of about 1 second. Now, it's all about simple arithmetic afterwards. What we do is divide the 1 minute into 4 parts. And our goal is, of course, to accomplish to just less or equal than 2 connections per minute. And we have assumed 15 seconds per connection, so this is very easy to count. Initially, from time 0 to 15, we open 1 connection. Then, from 15 to 30, there is a time period where Ncrack is at rest, and we use the timing option connection delay that we had mentioned before. Then, Ncrack starts opening a new connection again, and it finishes at time 45. And then it's at rest again for 15 seconds. And by this way, we have bypassed the firewall. Then the command for accomplishing this is the following. Of course, we write Ncrack to execute Ncrack. The same thing as before, as far as the host name and the SSH module and the port is concerned. And we specify a maximum of 1 parallel connection. We want the connection delay at the far left to be 15 seconds. And now there's also another nifty trick that we'll present here, which is the timeout. As we said before, we want to be as stealthy as possible. So we specify that Ncrack will be running only for 6 hours, and specify this by the TO option, which means which is short for timeout. And this will make Ncrack quit after 6 hours have passed. Now, of course, the cracking session might not have finished after 6 hours have passed. The cracking sessions are usually very, very long. So what we can do, when we can also specify the ---- save option, which will make Ncrack save the current session to this file called SSH session. Then we can use a scheduling application like cron in Unix and call Ncrack with the ---- resume option and the file that we have saved the session. And of course we specify cron to schedule this application only during the night at 9 p.m. because, as we said before, we want to do this only during the night. And this is very useful because it will just keep doing this as long as it needs to finish all the cracking session. And there's also one other option here that we have specified, the -f option, which just means that quit cracking after you have found one credential. And you don't need to check the rest of the username and passwords in your lists. And you can also specify, of course, your own password list using the -p uppercase letter. Of course, the same holds for specifying your username list and so on. Now, some things about the Ncrack SSH library. The SSH library wasn't, we didn't take any ready library. Rather, I wrote my own, and I used the original OpenSSH code to do this. Now, the OpenSSH code uses its own sockets, its own socket operations, and thus, since Ncrack uses NSOC to do all of its socket network operations, I needed to hack the parts that had the socket code in OpenSSH and substitute them with Ncrack callbacks. And this was quite a strenuous task, but it was also quite educational because I saw how one of the most popular servers out there is implemented, and I also saw a lot of things about how the SSH protocol works. And the bonus thing about using OpenSSH, the positive things, are that there are many buggy SSH servers out there. These are usually old implementations that might have some certain peculiarities. For example, there might be some servers that expect to receive an SSH packet that has a certain flag active, a certain bit active, or whatever. And if they don't receive this packet, then they might drop the connection. And OpenSSH, because it's really robust, it has taken account of all these peculiarities and has code that manages to bypass them. It has many workarounds for this. So we leverage this functionality of OpenSSH and we use it for Ncrack. In addition, there are also many other types of authentication which are more obscure in SSH, and we can also use the OpenSSH code for them immediately without having to reinvent the wheel as far as these are concerned. Now, another very important thing is the order that you test the usernames and passwords. Now, the usual order in most of the authentication cracking tools is, suppose you have the username list that you see here and the password list that with these passwords. And the username list is guest and root, and the password list is 1, 2, 3, 4, 5, test, foo, and bar. And most network authentication cracking tools do the opposite of what Ncrack does. For example, they test the initially they iterate over the password list and then over the username list. So for example, they first use the guest, and then they test all the passwords. So guest 12345, guest test, guest foo, and guest bar. But this doesn't really take advantage of the fact that password lists have been sorted according to frequency rate. So in the first line, the first password is the most frequent. For example, 12345 is one of the most frequent passwords out there. So in order to take advantage of this, you need to do it in the opposite order. So when you have these lists, Ncrack does the following. It tests guest and 12345, then root, which is the second username, and 12345, and so on. And of course, if you want to do the opposite, you can specify the passwords first option in order to do it in reverse order. Now, the problem with SSH is that it doesn't allow changing the username when you are in the same connection. So if you want to do this, if you try and do this in the default order, when you have tested guest and then 12345 and then change the username to root and the password 12345, because you have changed the username, SSH will tell you it will drop the connection, and this is a problem. So what you have to do is initially you send, of course, the reconnaissance probe to learn the maximum authentication attempts per connection, which is, suppose there are 3 for our example. The administrator can configure this to be whatever value he wants. And suppose you have this username list and password list, and suppose that you have 4 parallel connections. Then what you do is a mixed mode of order. So you test the guest, and which is the first username, and then the first password 12345, and then you keep the same username and test the next 2 passwords, which are test and foo. And you do the same thing for the rest of the connections, so that the SSH doesn't really, can't really drop the connection this way. And this is very important. Now, some other thing to remember, and this is very handy when you do penetration testing, is that sometimes certain services purposefully insert a time delay between each authentication attempt. So for example, I remember FileZilla. Whenever you send a username and password, it waits about 3 seconds or maybe more before you can test the second username and password. And in this case, it may be better to open many connections with each doing only 1 authentication attempt per connection, and then immediately close. In this case, the TCP, the 3-way TCP handshake, the time that it takes is less than the time delay that the service imposes. And this is very frequent. So in this case, you can just specify that the authentication attempt, the AT timing option, is 1. So in this case, Ncrack will just close the connection immediately, and it will be much faster. Now, some things about the remote desktop protocol. This was one of the most strenuous tasks of last summer. It almost took 1.5 months to implement, but it was worthwhile. One of the 2 reasons is that no other tool nowadays can really do RDP cracking. And this is because TS Grinder, which only works on Windows, is quite broken and buggy. It doesn't even work, if I remember correctly, for cracking Windows XP and above. And there were also some desktop patches, but they're really slow and don't really work on Vista and above. So the implementation of the RDP protocol took that much because I had to go through all the documentation of the RDP protocol in the official Microsoft website, see how this works. And there were also very peculiar cases, and one of the most of the most of the strangest cases were when the RDP server just dropped the connection whenever there was a certain bit active, and this bit had to do with the bitmap compression, which is completely irrelevant, of course. And in order to find this out, I had to compare bit by bit, byte by byte, the output, the Wireshark output of our desktop, and compare it with my own, with Ncracks. And this was quite a task to do. I had to do this for packets that were many, many bytes long. And you can see here the proof of the RDP hell. All these packets are required just to do the authentication, all of them. And another special case was that until Windows XP, everything was normal. And by normal, I mean that whenever you sent an authentication credential pair, it told you that you have failed using a certain string, a certain text string. And this was quite easy to parse. You just had to find in your packet that there was a certain string that told you that you have failed, the username or password is incorrect. But they changed that in Windows Vista and above. The fact was that they embedded this information in the graphical part of the R desktop. I don't know why they did this, but in this case, you couldn't just search for the string that the username or password is false, is incorrect. So what I had to do was try and search for a magic pattern, a pattern that would be in all versions of Windows from Vista and above, Windows 7 and 2008 server, and so on. And I found out after some search and of course a lot of Wireshark debugging that the magic pattern were the coordinates of either the button, OK, or the X button. I never really found out which of them, but they were the same always. The coordinates, which you can see there, these are the struct values, were always the same whenever you had failed an authentication attempt. So, of course, the resolution always plays a big part in this. But the good thing is that because the coordinates may be relative to the resolution of the rest of the window, but the good thing is that the client sends the proposed resolution. So Windows can really trick you and change the coordinates. So these coordinates for the certain resolution that you send are always the same. And by this way, you can determine whenever you have failed an authentication attempt. Of course, for the case where your attempt was successful, there is a default way to do this. So fortunately, that wasn't quite a task. And finally, some Ncrack features that all pen testers will adore are the following. All of you that have used Nmap might know the two basic output formats. The one is the normal output, which is human readable, and the other famous one is the XML. Ncrack can be fed these Nmap files, either the XML or the normal output files, and automatically choose its targets based on which ports were open and which protocols it of course supports, because Ncrack can't crack everything out there, and some protocols don't even really have the notion of authentication in them. And you can also use the Nmap notation in target and service specification, all kind of magic things there that you know. For example, wildcards, subnet masks, and so on. There are also high-quality username and password lists shipped in with Ncrack, so you don't really need to even specify your own list. Ncrack has many of them by default, and we have compiled these lists by combining publicly leaked password lists, for example, from MySpace and PHP bulletin board. And there were also some other password lists from John the Ripper, from Solar Designer. And of course, there is absolute portability in all major platforms. You can run it in Windows without SiegeWin, just an executable like Nmap. It works on every BSD, Linux, Mac OS X, all the major platforms. The other thing is the resume and save session that I had demonstrated already. And there's also IPv6 support and interactive output, which is the same as Nmap, which you can just with which you can just press spacebar while Ncrack runs. It will send out an output that says how much of the authentication session has been completed and so on. And you can also decrease and increase the verbosity level and the debugging level and so on. Now the resources for Ncrack are the following. The official site, of course, it belongs to Nmap. The manual page, which is quite extensive. I have also written a developer's guide, which explains step by step how you can write your own module. And I also expect to see many developers to write their own modules and contribute to Ncrack. We have already received modules from the community. In my site, I have also a certain section that focuses on Ncrack. I have uploaded the status reports from Google Summer of Code, from the 2 Google Summer of Codes that I have participated in writing Ncrack. And there's also the paper about how I built the OpenSSH library, which describes the whole process of hacking OpenSSH code and how I implemented this. Of course, I advise you to always download the latest version. For example, the ---- save option is only available in the latest SVN version. You can't find in the stable release, because I had recently added this feature. And of course, you can download it from the SVN repository. So that's all. If there are any questions. Okay, thank you.